So now that we know how to differentiate the natural log, we can begin to apply this into a range of different situations, which we've seen before with derivatives. And one of them, the first example that I've got here, is for us to find the coordinates and the nature of any critical points for the function f of x equals x squared times the natural log of x, okay? And we've got a strict domain here such that x has to be larger than 0. So how would we solve this problem? Well, if we want the coordinates and the nature of critical points, we need to start by solving when the derivative is equal to 0. So if we differentiate this function, we have a product rule happening here. So if we do the product rule, we'll keep the first part the same and differentiate the second part. Now we know that when we differentiate the natural log of x, we know that we just get 1 over x. And then we add on our derivative of the first part and keep the second part the same. And we need this to be equal to 0. So with a little bit of algebra, this first bit here simplifies to just x plus 2x times the natural log of x has to be 0. Now I can factor out a common term of x here, so I get 1 plus 2 times the natural log of x needs to be equal to 0. Now there's two possible solutions here. Either x is 0, so looking at that part there, or looking at this bit here, 1 plus 2 lots of the natural log of x has to be equal to 0. Now, the strict domain says that x has to be larger than 0, so this solution here is a no-go, but the one on the right could potentially work. So if we solve this equation, 2 lots of the natural log of x is equal to minus 1, so the natural log of x has to be negative a half. And if we convert this to indice form, this is saying that x is equal to e to the power of minus a half. So if you just convert that logarithm straight into the indice form, so x is 1 over the square root of e. So that there is going to be a critical point. Now, if I want the coordinates for that critical point, I need to put that back into f of x. So f of 1 over the square root of e, I get 1 over the square root of e all squared multiplied by the natural log of 1 over the square root of e. And if we simplify this down, this bit here just becomes 1 over e. And the natural log of 1 over the square root of e, well, we saw that happening down here. Okay, so that's equal to negative a half. So negative 1 over 2e. So our critical point has the coordinates 1 on root e coming from the x coordinate and the y coordinate negative 1 over 2e. So that there is a critical point. The other part of the question though, we have to find the nature, and we can do this by using either the sign test or the double derivative test. Now you can choose, but I'm going to go with the double derivative test. So we saw that this bit here was our first derivative. So if I want the second derivative, I've still got I'll just differentiate this x here, gives me 1. But now I've got a product rule happening again here. Okay, so we can product rule out, that's okay. Keep the first part the same, differentiate the second bit, add on the derivative of the first part multiplied by the natural log of x. So we get 1 plus 2 times the natural log of x, which is just 3 add 2 lots of the natural log of x. Okay, now we need to put our x coordinate into here for the double derivative test. So when we do that, we're evaluating the double derivative at 1 over the square root of e, which is 3 plus 2 lots of the natural log of 1 over the square root of e. Now we get 3 plus 2 lots of, remember this is minus a half, and so we get 3 minus 1, which just gives us 2, and that is greater than 0, therefore we have a minimum. So our coordinate here for our critical point is a minimum. So that would be how you could tackle that sort of problem. Now we'll have a look at another one. So here we have a rectilinear motion problem where we're going to apply our derivatives, okay? And we have a particle which has the following displacement function, and that is that x of t is equal to negative sine of t times the natural log of t. And we're looking across this domain here from t going from 0 to 4. And let's let t be in seconds, and our displacement x can be in meters. So 4 parts to this question. Part A, when is the particle at the origin? Okay, so the particle will be at the origin when the displacement is equal to 0. So when x of t, which we know is negative sine of t times the natural log of t, that has to be equal to 0. Okay, now that can happen either when sine of t is 0 or when the natural log of t is 0. So 2 options there, okay? If we first start on the sine of t being 0, that can either happen at 0 or pi, okay? We can't go any further because we're restricted in our domain from 0 to 4, okay? But the natural log of t, that will be 0 when time is equal to 1 second. So the answer to part A would be when t is 0, 1, or pi seconds. Okay, now part B here, what is the velocity function for the particle? Well, to get the velocity, v of t, we have to differentiate our displacement function, okay? And we're going to have to use a product rule here. So if we start with the first part, we'll keep the first part the same, negative sine of t, and we'll differentiate the second part. Now this is where we have to differentiate our natural log function, and the derivative of the natural log of t is just 1 over t. Add on the derivative of the first part, which is negative cosine of t, times by your second part, which is the natural log of t. Now if we sort of simplify this down a bit, we get negative sine of t over t, take cos of t times the natural log of t. And that would be what your velocity function is equal to. Now, part C asks when the particle is stationary. And the particle is stationary when the velocity is 0, i.e. it's not moving. So if we take our velocity function, which is our v of t, which we just calculated, to be negative sine of t over t, take the cosine of t times the natural log of t, that has to be equal to 0 to have a stationary particle. Now, this is going to be incredibly difficult to do by hand, so this part of the question would allow for the sole facility of some form of calculator. And the answer that you should get is either that t is 0.35 and t is equal to 2.13 seconds. Okay, now there are more solutions to this equation, but again, we have to keep in mind the restrictions of our domain that t sits between 0 and 4. And that should yield you these 2 solutions here. And finally, probably the toughest part of this question, the total distance traveled by the particle. So we have to take into account all the different time frames. So what I mean by that is if we look at our time, we start at 0 and then we go up to this point where the particle becomes stationary, and the first time that happens is at 0.35, okay? And then we go from 0.35 to the time when the particle is again stationary, so at 2.13. And then we go from 2.13 up to the time again, the particle is never stationary again before we hit the end at 4 seconds. Okay, now the importance of this, remember, is because if we have our displacement and our time, okay, so that's our graph, and let's say that it looks something like this, right? If I want the total distance traveled, I cannot just look from start to finish because that's only going to give me that little bit of distance there. I have to go all the way up to here, to the point where it becomes stationary, and then come all the way back down again. So that's the importance of breaking this time frame up. Now, if we erase that little drawing, we want to look at the displacements at each of these times. So your x of t. Now remember, your x of t function is stated up here as negative sine of t times the natural log of t. Okay, so if we put in time as 0 into that, we will get 0. And if we put in 0.35 into there, we actually get 0.36 pop out. So what that's saying is that in the first 0.35 seconds, we've gone from 0 displacement up to 0.36 meters of displacement. We've then gone from 0.36 meters of displacement. If you put 2.13 in, you would get negative 0.64 meters of displacement. And then we've gone from negative 0.64. If you put the 4 into your displacement, you would get 1.05 meters. Okay, so again, the importance of breaking this time frame up is we've gone from 0 up to 0.36, down to negative 0.64, and up again, all the way up to the top at 1.05. So if you'd just gone from the start up to 1.05, you wouldn't have all of this up-down motion happening. So that's the critical reasoning behind why we have to break the time frames up. Now, if you look at the total distance traveled in each of these time frames, so from 0 to 0.36, we've gone 0.36 meters. From 0.36 to negative 0.64, we've gone a whole 1 meter. And from negative 0.64 to positive 1.05, we've gone 1.69 meters. So the total distance traveled, if you were to add these up, is 3.05 meters. So that would be how we would tackle this rectilinear motion problem. Again, part A and B we can do without a calculator, but part C and D, for part C you would definitely need some form of solve facility, and for part D, just a scientific calculator would work fine there. So that gives you an idea behind the applications to being able to differentiate the natural log function.